Greetings everybody. Let's continue along with our discussion of Green's theorem. And so just for a statement of that theorem so that we kind of remember where we were at, we had a region D, and the boundary of that region was going to be a piecewise smooth, simple closed curve, and we're going to give it a positive orientation as we parameterize it, so that our region, as we parameterize it, is always going to be to the left as we are tracing out that boundary. And so if we have P and Q are continuous, have continuous partial derivatives on an open region that contains D, then the curl of that vector field PQ, dA, so the double integral over the curl of that thing, was going to be equal to the line integral of that vector field around the boundary. Now, if we wanted to go through a full proof would be justified in doing kind of a deeper dive into things like differential forms, and then we obtain a result for which Green's theorem just then becomes a special case, and this kind of bigger result is what's known as Stokes theorem. Now, we're going to meet Stokes theorem a little bit later, and so we might come back and do a supplemental proof kind of going through the differential forms and kind of seeing how we can then derive Stokes theorem, prove Stokes theorem, and then get Green's theorem as a consequence by going through the proof that Rudin presents in his book, but we'll kind of do that maybe in a later video. So until then, what we can do is kind of let's motivate this thing by way of an example. And suppose that we've got our region D, and we're going to start off with a simple characterization of that, and that D is going to be the region between two smooth curves, G1 on top and G2 on the bottom. And the left and right are going to be bounded by just these vertical lines. So that we could characterize D as just the set of points x, y, with x going in between A and B, and y as being in between these these smooth curves G2 and G1. So if we can look at this thing, then our boundary is really going to have kind of a shape that looks something like this, more or less, where we've got, kind of break it up into those three parts. We've got a curve C3 from right to left on top. We've got a vertical curve for C4. We've got C1 going along the bottom from left to right, and then we've got another vertical segment, C2, so that our boundary actually consists of C1 plus C2 plus C3 plus C4. Now, if we start looking at the double integral of the partial of P with respect to y for dA, so the negative of that thing, then we can just calculate that pretty simply as it's the region between G2, the double integral from G2 up to G1, an A to B of the partial of P with respect to y of dy dx. Well, if we do one integration, since that's derivative, our fundamental theorem of calculus is just going to tell us that that's P evaluated at the upper limit minus P evaluated at the lower limit. And so we've got these x values. And so we can take those and kind of split them up. So we've got negative the integral from A to B of P of x G1 of x dx plus the integral from A to B of P of x G2 of x dx. And so now let's bring our curves into this thing. So what do we have here? Well, the parameterization for C1, remember that this one was just going to be our bottom curve, so we can just do T and G2 of T, since y is just a function of x that we have there. And so this gives us this parameterization. If we then compute the line integral of C1 of P of xy dx, then we take everything, plug in our parameterization, dx then becomes dx dt dt. Well, dx dt for our parameterization was just 1 because it was just the constant t, or just our plain linear function t. And so what that gives us is that our line integral over C1 is just that first part, our integral from a to b of p of t g2 of t dt. Now, if we do the same thing kind of for the parameterization of the curve on top, that we just do t and g1 of t for the y value, then the line integral over the negative, so the line integral over opposite of our orientation for C3 just becomes the same thing, the integral from a to b, p of evaluate the x function, evaluate the y function for our parameterization on our curve, dx dt again becomes 1, and so we just end up with this. So our curve C3 with that negative with the opposite orientation on it gives us our second integral. Now, since the curves C2 and C4 are really just vertical lines, we can parameterize those with just for our right side, it's just our x value is at a constant b. For our left side, our x value is just a constant a, and then our y values are just kind of those linear functions, so that when we compute our dx for our dx dt, we get 0 out of that. And so what ends up happening is that, and we kind of go back to the beginning now, our negative of our double integral of d of partial p y dy, we had this expression. Well, we separated that out. So this one, this first integral became the reversed orientation line integral for our top. So we had this negative on the outside, so that just becomes the integral over our top. Plus, we had the integral over our bottom, that was our C1, and then we can just slap on a couple of zeros that don't change anything, and those zeros are our integral over C2 and our integral over C4. So we put all of those together with our properties of line integrals, and so we get our integral over our entire boundary is just going to be our p dx. And so for this one, it kind of gives us our first part in Green's theorem. So we've got our partial p, partial y. So again, kind of going back to the beginning of that one, we've got our partial p, partial y. So now how do we get this partial q, partial x? So stay tuned for that one, and I will see you guys in the next video.